All right, so I think let's start on this makeup lecture. So this is really making up for next Wednesday. We'll have a class next Monday, but we won't have class next Wednesday. All right, so I hope everybody have seen that project 1 is over on the internet in learning modules since Wednesday night, and the due date is there. I think you have it's 12 or 14 days. 14 days, yeah, since basically 2 weeks. It'll be due on the Wednesday, not the next week, but the week after next week. All right, so today let's continue on studying finite difference. And at the end of the last lecture, we have started to look at how much error is there, not only in the approximation of the finite difference operator, but also in the solution itself. So the difference is that the truncation error is defined as the difference between the analytical derivative of a function minus the discrete operator operated on the same function. That's our finite difference operator. The same function, so the w that appears in the derivative is the same w on which you take the discrete values on the grid points and plug into the finite difference operator. But the solution error, so this is called the truncation error, that's very different from the solution error. The solution error is defined as wi minus, let's call it W analytical, W superscript A, okay, at I delta x. That's solution error. So here we are looking at two completely different functions. One function that is obtained by analytical solving the differential equation, another function by solving it using our discretization method. All right, to make the point a little bit clearer, let's actually look into the case, the sine functions we demonstrated numerically in the last lecture. Let's look at if the solution started as a sine function, how would the error evolve? Okay, so the example is over here. So let's take an example. So the example is the following. If my w at x and 0, which is equal to w analytically at t equal to 0. So we start analytical and numerical solutions at exactly the same function. It's equal to sine of 2 pi kx. Okay, x is between 0 and 1. We also impose periodic boundary condition. So we force w0 to be always equal to w1. And also other derivatives are. As many derivatives are also matching as you need for the differential equation, for the purpose of the differential equation. So let's start with such solutions, and we can solve the equation numerically on paper, and we also solve it analytically as we did in the first lecture on paper, and see what the solution would look like. Okay, analytically, we already know what the solution is going to be like, right? The solution W analytical x and t. We know that from, I think we did this already twice. We know that if we plug the analytical solution into the differential equation, when we take the second order derivative, it's still a sine function, but it's a minus constant times a sine function. So that means the shape of the function stays as the cosine, but its magnitude is going to decay exponentially. And the rate of the decay is minus 2 pi k squared times t, sine of 2 pi kx. You can easily plug this into the analytical differential equation and show that it satisfies partial w analytical, partial t is equal to, here kappa is equal to 0, so the second derivative of wa with respect to x. Okay, So that's our analytical solution. We already know that. What is new in this lecture is, what if you solve the same equation but numerically using our finite difference approximation, but also starting from the same initial condition? What would it look like? Would it still be maintaining a sine function? Would it still decay exponentially? Would the rate of the exponential decay be the same? So let's find out. All right. So how do we find out? We actually do the same thing. We try to plug the sine function not into the second order derivative, but to our approximation of the second order derivative. Okay, so that is what is wi plus 1 plus wi minus 1 minus 2wi divided by delta x? What is if wi is equal to sine of 2 pi k times I delta x? And of course, wi minus 1 is also equal to sine of 2 pi k I minus 1. Well, let's just write I delta x minus 2 pi k delta x, right? So that's I minus 1. Question? Oh, delta x squared. Thank you. Thank you. Yeah. I like when people point out my mistakes as soon as possible. That's great. Okay, so I plus 1 is then we are basically adding 2 pi k delta x into the sine, right? So this is all inside the sine function. Okay, the rest is algebra. The rest is really trigonomic function algebra. And the algebra is actually a little bit easier in this case. If you, instead of writing sine and cosine functions, you write exponential of imaginary functions, right? So in this case, let's actually write it slightly differently. So we'll write wi as the imaginary part of e to the I. Here, because we use the I as the index, let's make sure our notation is clear. Let's actually use j, all right, as the square root of minus 1. So j is square root of minus 1. So exponential of j times 2 pi k I delta x, right? And I plus 1, I minus 1, etc. are the same. All right, then wi plus 1, our discrete operator when operated on this analytical function for which we know the analytical solution is going to be, let's write it down, delta x squared. We have wi. So all of them are the imaginary part of exponential functions, right? And the first one, we have exponential of j, 2 pi k, I delta x, okay, plus j 2 pi k delta x. So this is wi plus 1, the value of the sine function at the right hand side grid point. Also plus the same thing, but on the left hand side grid point, minus j times 2 pi k delta x. So that is at I minus 1. So I minus 1 is this, right? And finally, we minus 2 times wi, which is just e to the j 2 pi k I delta x. Any questions on this? No?